So we're looking at the things that led to the discovery, or the discovery of quantum mechanics. What led to quantum mechanics, and some of those were discoveries, and some were understanding experiments that weren't previously understood. And we start in 1897 with J.J. Thomson discovering the electron using the newfangled vacuum devices called cathode ray tubes. But what J.J. Thomson actually discovered was some kind of particle that had a charge to mass ratio of Q over m, and he was able to measure this. He was able to measure this quantity Q over m, but he could not independently measure Q or m using his experiment. So the next experiment we're interested in was the millikan oil drop experiment, which came about 15 years later. The millikan oil drop experiment. Incredibly painstaking observation, Millikan was able to determine the charge of an electron. Hence, once determining the charge of the electron, we can determine the mass of the electron. So how did Millikan do this in the oil drop experiment? What Millikan did was he had this simple apparatus. Two parallel plates, turned out to be round, but it doesn't matter. Parallel plates with a constant electric field, E, between them, right? How does he get that constant electric field? Well, he just puts a voltage on those plates, and we know that, if we put a voltage between the plates and they're separated by a distance h, that we know that the electric field, the magnitude of the electric field is equal to delta V over H. Which again comes from, I keep on leaving off this minus sign, comes from the definition of potential difference, minus E dot dr. Okay, that's just the magnitude of the electric field in relation to the quantities that Millikan was set. So he has this parallel plates. Now this apparatus is probably tabletop sized, about the size of a big pot that you'd put on your stove. And there's a hole in the top of the apparatus. And what he did was he put oil drops into this hole. But they were charged oil drops. So he puts oil drops into the hole. They're not electrons, they're oil drops. So let's go ahead and choose an oil drop color. Okay, so we've got oil drops that he drops into this hole. And those oil drops are charged. Now, how does he get them to be charged? What he does is he subjects them to a radioactive material, which will then rip off some of the electrons. He ionizes the oil drops, ionizes them, right? He subjects them to something that takes away, right? An oil drop typically might be a neutral charge, but you subject it to some radioactive material, which are reasonably easy to come by, and not necessarily dangerous or anything, that will ionize the oil drops. So the oil drops are charged, but we don't know how much they're charged by. They're just charged. They all have different charges. And so what he's able to do is Millikan is able to observe these oil drops as they fall, and he'll pick an oil drop, and he will vary the potential difference until he gets that oil drop to levitate. Okay, so I just realized I'm pretty sure I drew this electric field in the wrong direction to make the oil drops levitate. In other words, the electric force is going to be upwards, has to be upwards on a given oil drop to balance out the gravitational force. That's why they fall. They fall because of the gravitational force. So the electric force has to balance out the gravitational force. And you say, but they're negative charged oil drops, and so therefore they will be pushed against the field. But no, if they're ionized, we're taking away electrons. They're what's called holes, still with charge E, but with charge plus E. Really what you're doing is you're looking at the charge of an absence of electrons. And so it's a positive charge. So I think that the electric field is actually up, not down. But regardless, we just care about magnitudes when we're doing the calculations. So let's look at a single oil drop. Let me just say, as I'm writing this, is that what Millikan did is he just did this measurement for thousands and thousands of oil drops, painstaking measurements. What he did was he made them levitate. In other words, if the electric force is up and the gravitational force is down, those are the only two forces on the oil drop. Ask, what are the forces on the oil drop? When it is in equilibrium, that is it. In equilibrium, Fe minus mg equals 0. That's what it means for there to be equilibrium. So therefore, QE equals mg. Now, if he then lets the oil drop fall, there's an additional force. And what's the additional force as the oil drop falls? Let's say he just turns down the electric field a little. He doesn't get rid of it. He lets the oil drop fall. There's an additional force, and that is the frictional force, the air resistance. And these are small, little, light oil drops, so there is indeed a frictional force or air resistance pointing upwards as well. But when they're in equilibrium, he can adjust delta V until they're stationary. And so then he can, therefore, he knows QE equals mg. Therefore, since he is adjusting delta V, we can just write that Q delta V over H equals mg, and therefore Q, the charge of the oil drop, not the charge of the electron, the charge of the oil drop, is mgd over delta V. Okay, so, sorry, that's in the corner. So what does that tell us? Well, what that allows millikan to do is to measure the charge of that particular oil drop. Remember, what's the charge of the oil drop? He has taken away some number of electrons. We don't know how many. So the charge of the oil drop might be 1e, 2e, 3e, 10e, 100e, I don't really know. But it might be any multiple of e. Okay, so that's what Q is. Q is some multiple of E, where E is 1.6 times 10 to the minus 19 coulombs. What is M? What is the mass here? The mass is absolutely not the mass of an electron. What is it? It's the mass of the oil drop. Now, how does he know what the mass of the oil drop is? This is what's kind of amazing. How does he know what the mass of the oil drop is? What he does is he levitates the oil drop in order to get, in order to figure out what delta V is, in order to get this equation. But then he lets the oil drop fall, and he uses this, the friction, and air resistance is very well understood, and he can use the speed of fall of the oil drop, and we won't go into those details, to determine M. So he's able to determine delta V for levitation, so that this equation at the bottom is true, and then he's able to let it fall, measure the speed of fall, in order to apply the air resistance and that allows him to figure out what the mass of the oil drop is. So he's measuring delta V through levitation and M through letting it fall. And once he measures those two things, what millikan then has is he knows that the charge of the oil drop is, again, mgd over delta V, mgd over delta V. And what he recognizes after making thousands of these measurements and analyzing the data, painstakingly looking closely at the numbers, he recognizes that the charges that he's measuring, that these quantities, which are all different for all the different oil drops, but they're all some integer multiple of some smallest number. That's what he recognizes by looking at the data, that there's some integer multiple, so he's measuring all that and then recognizing that that is some integer multiple of some smallest number. Hence, he is able to determine what that smallest number is and determine that that must be the smallest possible charge on an oil drop. So he is able to measure the smallest possible charge on an oil drop, and what he measures is Q smallest is equal to 1.6 times 10 to the minus 19 coulombs. And hence, that is the charge of an electron. Pretty ingenious and difficult experiment to do. So just to understand how the millikan oil drop experiment works, let's just make sure we understand that, and let me give you a different example. Let me say I have a lot of marbles, and different amounts of them are sealed in different containers. I can't access the interior of the container. How can I find the mass of a single marble? The way to find the mass of a single marble is to go ahead and measure the mass of each container. Let's say that the mass of container 1 is, we put it on a scale and we find that that's 10 grams. The mass of container 2, which has my marbles in it, is 3.5 grams. The mass of container 3, etc. So look at these numbers and tell me what the mass of a marble is. Well, you can actually only tell me what, you can give me an upper bound of the mass of the marble, right? Because we can say, well, it can't be bigger than 3.5 grams. But this is different than 3.5. The difference between 3.5 and 4 is 0.5. So it can't be bigger than 0.5 grams. If all my, we are assuming all the marbles have the same mass. So it can't be bigger than 0.5 grams. Let's look at the rest of these. 7. Yeah, so we say that it's the mass of the marble must be less than or equal to 0.5 grams. How is that helpful? Because the mass of the marble could be 0.1 grams, and there could be 5 more marbles in container 4 than there are in container 2. Well, that is true. That's why we want to increase the number of containers. Instead of doing 5 containers, let's do 1,000 containers. Or 10,000 containers. And then the chances of having a bunch of containers that only have one marble difference is much larger. And we can really, we can be pretty sure that the smallest difference between containers is the actual mass of the marble. So if we have a lot of containers and we still find that there's no smaller difference between any 2 containers than 0.5 grams, then we can. So what millikan was able to do, what J.J. Thomson was able to do was to measure the charge to mass ratio of this thing that is in the cathode ray. But what millikan is able to do is to show this concept of quantization, that the smallest possible charge on an oil drop was 1.6 times 10 to the minus 19 coulombs. That's what he was able to show, is that's the smallest possible charge on an oil drop. And yeah, he could be wrong, but he was able to show with some confidence that the smallest possible charge on an oil drop is 1.6 times 10 to the minus 19 coulombs. So that is the start of this concept called quantization. Have we defined quantization? Quantization. That charge is quantized. What that means is it comes in blocks. It comes in a smallest piece. It can't be cut up into any smaller piece. That's what additionally millikan was able to conclude through his painstaking experiment, is that charge is quantized. Now, since then, we have certainly discovered that electrons are still the smallest piece of matter that we can find. We can't get anything smaller than an electron. In other words, an electron, as far as we know, is not made up of anything else. But there is something with a smaller charge, and that is a quark. Except to recognize that quarks do not live naturally in nature. They come in threes. Quarks are not naturally independent. They come in threes, and 3 quarks together make up the charge of an electron, even though electrons are not made of quarks. Don't get me wrong. Electrons are not made of quarks. But neutrons and protons are made of quarks. And neutrons are neutral, and protons have a charge of plus 1e. I've summarized it better here. As far as we know, electrons are fundamental. They're not made of quarks. We can't break them up. And that they have charge of minus 1e, where e is 1.6 times 10 to the minus 19 coulombs. A neutron is made of 3 quarks. Each of the quarks has 1/3 e charge, or 2/3 e charge. There's the down quark. The down quark has a charge of minus 1/3 e, and the up quark, which has a charge of plus 2/3 e, and the neutron is made of 2 down quarks and 1 up quark, whereas the proton is also made of 3 quarks, but is made of 2 up quarks and 1 down quark. So the proton's total charge is plus 1e. So the proton and neutron are not fundamental particles. The electron is, as far as we know, a fundamental particle. We may in the future find that it's not, but as far as all the best experiments show currently, that you can't break it up into any smaller particles. Neutrons and protons, you can break up into smaller particles. But what I do want you to recognize with those quarks is that quarks are not naturally occurring by themselves. Neutrons and protons are, but you don't find quarks in nature until you do these, by themselves, until you do these experiments to break them up and measure them in these huge accelerator experiments. Okay. Fundamental means, as far as we know, can't break it up any smaller. It takes up, and actually they take up no space. That is an important thing to understand about electrons, is electrons actually have no size. They take up no space. As far as we know, as far as we can measure, to the extent that we can measure, they take up no space. Point particles, true point particles.